All right, so today, what I want to do is just quickly wrap up the reviewing with just a very brief review of trig functions. There's some notes here that you can read, but as far as we're concerned, really all I want to do is review the basic functions, and then we can dive into limits at long last. We've been reviewing a lot, and this is great, but we do have other work to do. So just as a quick overview, and you can read the rest of these slides later on if you want to, but these are the six basic trig functions: sine, cosine, tangent, cotangent, secant, and cosecant. Now, these will pop up quite often in calculus. So at the very least, we want to make sure we remember how they're defined. And then as we go along, for example, in the limits chapter, we'll see how to calculate the limit of a trig function. When we start talking about derivatives, we'll see how to calculate the derivative of a trig function. So in other words, they're going to be there in pretty much every chapter that we cover. So first things first, you'll recall all of these, of course, are normally abbreviated. Let me just show you how that works. In case you've forgotten, for example, sine is abbreviated SI. And of course, you might remember that we often use the Greek letter theta to represent an angle. Okay, of course, that depends on what book you're using, but it's a fairly common practice to use theta to represent an angle. Then we have cosine. Okay, then we have tangent. Then we have cosecant. Actually, we'll start with secant. Cosecant, and then finally cotangent. And ultimately, all of these are just ratios. So if you can imagine, we have a right triangle. And here's theta. Here, this is a 90-degree angle. Recall that a triangle has 180 degrees altogether. So if this is 90, that means these other two angles have a total of 90. So what if I want to calculate these functions for theta? So if you recall from this triangle, this side is the adjacent side, or A. This is the opposite side, or O, and this is the hypotenuse. Okay, so H is the hypotenuse. O is the opposite side. And A is the adjacent side, which means the one right next to it. Okay, so the way you were normally probably taught to remember these is that you start by remembering the sine of any angle is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. And then finally, the tangent is the opposite over the adjacent. Okay, so if you have a specific triangle, let's say you know what the sides are, then you can actually calculate these directly just by looking at the triangle. Now, if you notice, there's still three more that we haven't mentioned yet: the secant, cosecant, and cotangent. These are just functions of these first three. For example, the secant of theta is the inverse of the cosine. The cosecant is the inverse of the sine, and the cotangent is the inverse of the tangent. Now, there are a large number of trig identities, which we will bring them up as we need them. Nobody expects you to memorize them all. It's a very long list. If you look in the back of any calculus book, you'll see a huge list of identities, but there are certain ones that will be important. The one I just want to remind you of is, for example, this one: the tangent, because of the way it's defined, is equivalent to the sine over the cosine. Why is that? Because if you recall, the sine is opposite over the hypotenuse. The cosine is the opposite, sorry, the adjacent over the hypotenuse. And of course, these cancel out and you're left with O over A, which is the same thing as the tangent. So that being the case, for example, the cotangent must be the cosine over the sine. Okay, so also a couple of other interesting results that we might want to remember. First of all, we want to make sure we remember the Pythagorean theorem. Let's try that again. So we just randomly label these A, B, and C. The Pythagorean theorem tells us that A squared plus B squared equals C squared. Okay. So as long as the A and B are the two sides and C is the hypotenuse, this is the Pythagorean theorem, and this tells us the relationship between the three sides. And it turns out that when you combine this result with the definitions I just showed you, that certain identities pop out. For example, this one, which we'll see on a fairly regular basis, this implies that the sine squared plus the cosine squared equals 1. And we can derive some of the others very quickly and easily from all of these different definitions. So as long as we remember these basic details, you should be in pretty good shape when we encounter these again in the following chapters in the book. Okay, so, but if you want to read through the rest of these slides and just quickly remind yourself, for example, I go through the definition of what an angle is. There's more terminology that you might have forgotten about. But and the idea, oh yeah. So here there's a discussion here about the relationship between degrees and radians. You recall that a circle has 360 degrees in it, and 360 degrees is the same thing as 2 pi radians. If you need to convert them back and forth, that's the relationship. You just have to remember this identity. Okay. What else might you find interesting here? I don't know. I think for now this will suffice. There's an interesting graph in here, though. You might want to take a look at it. This chart is a quick reference guide. You don't really need this if you have a calculator because you'll probably know the TI-84 and the others do have the trig functions built into them. But if you notice, they only have sine, cosine, and tangent because they expect you to know how these others work. Secant, cosecant, and cotangent. So they've got just the three of them there. And if you want to calculate the angle in degrees, at least with the TI-84, if you want to make sure you're calculating degrees, there's a button up here called Mode. And the upper left-hand corner. Now, unfortunately, this is backwards but right there is the Mode button. And if you look at it close to the top, in one of the rows, you have the choice between radians and degrees. You want to go to the one you want with your arrow key and then hit enter, and that will put it in that mode. Okay, so I don't know if you can see this or not. Again, it's unfortunately backwards, but you see it's flashing over radian. I've chosen degree. The other option is radian. And so that way, when I calculate, for example, the sine of 30, it's going to come back with, hold on, I keep hitting the wrong button, 0.5, okay? If you want radians, you, of course, switch to the radians mode. But you can calculate any trig function you want using your calculator. But this chart is very interesting because what it's doing for you is showing you for each of these special cases. If you notice, it's got the degrees and the radians next to each other. This first term in the parentheses is the cosine of that angle, and this is the sine. Okay, so if let's say I'm in a hurry and I want to know the cosine of 135 degrees, it's right there. negative radical 2/2. So, you know, this is fun. It's easy. It's useful, but if you have a calculator, you don't really need this. But anyway, we may need this later on. But in the meantime, now finally, at long last, we can get ourselves started with limits. And I think I've mentioned this a couple of times. Limits are the starting point of what we'll be doing because a lot of the functions that we will see afterwards are defined in terms of limits. Okay, so let's get this open up. And here we go, part A. So there's 3 parts to this chapter. And what we're going to do here is first introduce the notion of limits. And, at first it may seem a little abstract and a little complex and maybe hard to wrap your mind around. But once we've done a few of these, I think you'll start to see that it really is not that difficult. There are a lot of rules that we have to learn, special cases that we'll run into as we go along. But the concept itself isn't really that difficult. Basically, what we're aiming for is this. Imagine that you've got some function or other. Let's say it happens to be a quadratic function. And let's say that this is the point 2, -2. So the idea here is that as we're approaching from the left, meaning that we're going through the x values in an increasing manner and getting very, very close to x equals 2, as x gets closer to 2, f of x gets closer to -2. Okay. And then if we come from the right side, the same thing is happening. Now, by the way, the notation we'll use is this. As we're approaching from the left, we're going to put a little negative sign here to indicate we're coming from the left. And then if we're coming from the right, meaning the larger values of x, we're going to put this little, this little plus sign. It's just a convenience. It doesn't mean we're approaching -2 or +2. It means here we're approaching 2 from the left, meaning we're coming in this direction. So we're coming from the smaller values of x and getting closer and closer to 2. Over here, we call this approaching from the right. We're starting with the larger values of x, and we're getting smaller and smaller until we get very, very close to x. And since we're approaching the same point from both directions, we say that the limit of this function as x approaches 2 is -2. Oh, well, that's interesting. In other words, getting closer from either side. As we get close to x equals 2, f of x is getting very close to -2. So we're going to see the more formal way of writing this in the next slide. Just in the most general terms. So in our case, we had the limit as x approaches 2 is -2. Okay, so this is the limit. This is some constant that x approaches. Okay, now this, if you notice, there's no plus or minus here. The limit requires that as we get closer from the left and the right, we are approaching the same number. And if we are, then we say that the limit of the function as we get close to that point is equal to L. Okay, so here we're approaching from the left and the right, but since they both approach the same value, we conclude that the limit of this function as x approaches 2 is -2. Right? So that's what we're interested in. What value is the function getting very close to as x gets very close to 2? Now, now this one is a little tricky because if you notice, the domain does not include 1, and yet we're going to see in a second, we can still have a limit, okay? So here's what the function looks like, and you can see x equals 1. At x equals 1, there is a hole in the function. At 3. So if this point was part of the function, it would be 1 comma 3, but it's not. There's a hole there because this leads to division by 0. So the question becomes, can we have a limit there? In other words, if x approaches from the left, and as x approaches from the right, in both cases, the function is getting very, very, very close to 3, although it never actually hits 3. No matter how close we get, we're always getting progressively closer. The function, that is getting progressively closer to 3. Okay, so as x approaches 1, and this is from both sides, f of x approaches 3. So even though it never quite reaches 3, the fact that it's getting infinitesimally closer to 3 means that the limit of this function as x approaches 1 is equal to 3. So even though there's a hole in the function there, we still have a limit. Now, what I've done here is I've put together a small chart so you can visualize what's happening. This chart represents x approaches from the left. So you can see for yourselves that what I've done is I've started with -1, then get to 0, 0.5, 0.7. You can see we're getting really, really, really close to 1 without ever actually touching it. In the meantime, the f of x is getting very, very close to 3 without ever actually reaching it. It's kind of like, well, it's what you're trying to imagine is that you're getting very close to a specific point on the curve without necessarily actually reaching it. And so this is how a limit is defined. This is what we're getting infinitesimally close to. As x gets closer and closer and closer, the f of x is getting closer and closer and closer to the 3. And so as we approach from the left, the limit is equal to 1, 3 rather. And then here's the opposite case. X approaches from the right, or you can write it more formally as this. And so you can see x is getting smaller. It's getting really, really close to 1. And then the function is shrinking and shrinking, and it's getting really, really close to 3. And so they're both coming from both directions. The function is getting very, very close, or we can say infinitesimally close to 3. And therefore, the limit of this function is equal to 3 at x equals 1, that is. Okay, so this is how we wrap it up. The limit of this function as x approaches 1 is equal to 3, despite the fact that the function itself is undefined at 3. That's interesting. I'm getting extremely close without ever quite reaching. It's like the asymptote in a function. If you recall, for something like this, y equals 1 over x, as x increases, the function converges, gets closer and closer to 0. So we could say in this case that the limit is 0 as x goes to positive infinity. And on down here, as x goes to negative infinity, the function is also getting very, very close to 0. Okay, now sometimes there may not be a limit at all. Okay, it can happen. There's not necessarily a limit for every function at every point. Okay, under certain conditions, the limit may not exist at all. So here's a good example of this. We have the absolute value of x over x. Now, when you see the graph, you'll see right away why there's no limit. As we approach 0, as x approaches 0, look what happens. Here it is. So you can see as x approaches 0 from the left, the function is approaching -1. But up here, as x approaches 0 from the right, the function is approaching +1. Okay, this is +1 here. They're basically not heading in the same direction. In other words, they're not ending up in the same place. Okay, so this means that there is no limit. So in other words, when something like this happens, the two of them are different from each other. Okay. Um, Actually, I just realized I've written this slightly incorrectly. This is the way we normally write it. And since they're different from each other, meaning they're not heading in the same direction, that implies that the limit does not exist. Okay, so you see the distinction between the two cases here. There was a discontinuity in the function, and yet we're still approaching that 3 from both sides. Okay, so therefore this is our limit. Whereas here, we're approaching a different value from both directions. So that means there is no limit. And here's the tables, by the way, to prove it. You can see as we come from the left, and here as we come from the right, we're heading in a different direction. Okay. In fact, the function can only actually have the two values, -1 and +1. Okay. So this is a case where the limit does not exist. So, and by the way, this is not the same thing as saying that it's equal to infinity. It does not exist. We'll see cases where the limit is infinity. It can be positive, negative infinity, positive or negative infinity, but in this case, it simply does not exist. All right, so let's look at some more examples. Here's one. Now, clearly, this one also has a discontinuity in it. X clearly cannot equal 2 because that would lead to division by 0. So let's look at the graph. Oh, well, that's interesting. It's basically a straight line. Now, by the way, why is this happening? Because and so that means that you have this result. And then these drop out. And so what you basically have is a function which is a straight line except at x equals 2. It has that one discontinuity because of the way it's defined. Okay, so what we want to know is what happens as we approach this point, which is 2. So I think you can see what's going to happen here. Here, as x approaches 2 from the left, f of x is approaching 4. Over here, as x approaches 2 from the right, f of x also approaches 4. It never quite reaches it, but it gets infinitesimally close to it. In other words, we can get as close as we want to 2 from the left or the right. And that means that no matter how close we get, we'll get even closer to 4 without ever quite reaching it. So in this case, the limit of this function as x approaches 2 is equal to 4. In spite of the way it looks, the limit is equal to 4. Okay? And the tables, I've also included the tables. You can see visually that as we approach from the left, and as we approach from the right, in both cases, we're getting really, really close to 4, infinitesimally close, as a matter of fact. So no matter how much I get, like if I have one with like 100 nines here, here I'll be even closer to 4, but never quite reaching it. All right, now here's a wacky one. Absolute x minus 2 over x minus 2. What's going to happen here? Aha. Now, I think we already know what's going to happen here. You can see because of the way this is defined, there can't be a limit. Okay. This is -1 down here. This is +1. So as x approaches 2, actually, let me write this down here. Two from the left, f of x is approaching -1. And up here, as x is approaching 2 from the right, f of x is approaching, and so they're different. So as long as these two are different from each other, that means that the limit, if you notice I'm writing it without a plus or minus sign, the limit as x approaches 2 from either direction does not exist. By the way, the terminology here is that these are known as one-sided limits. And this one, the one that we're actually interested in, oh God, let me fix that. Usually, I mean, there can be cases where we're only interested in one or the other, but this is normally what we're interested in. This one is, as you can imagine, called a two-sided limit. When you hear the word limit, it normally simply means it's a two-sided limit unless it tells you otherwise. Okay. All right, then. And here's the tables to prove it. Okay, the limit does not exist. Okay, what about this one? And you can see the discontinuity will be at x equals 2. It's actually just kind of ridiculous coincidence that I picked so many examples where we're approaching x equals 2. It's not always going to be 2. Okay, just worked out that way. Oh my God, what's going on here? This looks like a catastrophe in the making. Now, by the way, keep in mind that symbol. This is a symbol app graph. It likes to draw the asymptotes in red. This is x equals 2 here. This is the vertical axis right here. You have to keep your eyes open for that. So as we get closer, now here's the interesting thing. What's happening as x is approaching from the left? The function is growing and growing and growing without limit. In other words, f of x is approaching infinity. Okay. As x is approaching from the right, oh, jeez, what did I do? Sorry, this should have been negative. Approaching from the left is the negative sign. Approaching from the right is the positive sign. But look what happens. The function just keeps growing and growing and growing. F of x converges to infinity. So you know what that means. The limit of this function as x approaches 2 is equal to infinity. So you can see what I mean now. That's very different from it being undefined. Infinity just means that no matter which direction we're coming from, the function is growing and growing and growing, and it is converging to infinity. So we can have an infinite limit, and we can also have a limit that does not exist. Okay. And the reason why this is happening is, again, because the left-hand side and the right-hand side are equal to each other. Okay. Or in other words, what I should say is the two one-sided limits are equal to each other. Therefore, this must be infinity. And it could also, if the curves were facing down, we would have a limit of negative infinity. That's also possible too. Yeah, and if you look at the tables, you can see what's happening as we come from the left. Look how big this number is getting. And on the right, same thing. Look how big the function is getting. It's growing enormously. So it is converging to infinity. Now, the next section is sort of a graphical introduction or overview of what exactly we're going to do with these limits, or how they're going to tie in with what's coming in chapter 2. What we're going to do now, these graphs, I didn't obviously draw these graphs. I took them from another source. There's no way I could draw these, but here, this blue is the function. Now, if you recall, a secant line crosses through a curve at two different places. The points we've chosen are A and X, A f of A, X f of X. So that secant line is giving us approximately the slope of this curve between the 2 points, but you can see it's not exactly right. So what we're going to have to do is imagine that these two get closer and closer together. So in other words, imagine now, I'll show you the next graph. They're closer. Well, here we have orange X, the original one, and here we have teal X, I guess. So you can see the slope of the teal line is a little different than the orange line, but it does appear to be a better reflection of what's happening on our original function, the blue curve. So by moving the X over closer to A, this line, the secant line, is a better fit to the function. And so what we have to visualize is that we're shrinking up the distance between these two and drawing new secant lines. Eventually, when we get close enough, the this secant line will actually represent the slope of the curve. Okay. And well, okay, now they've got another one in there. And you can see we're getting closer and closer and closer. And when the two are infinitesimally close to each other, what will result is the tangent line, meaning that it touches at exactly one point. So you're going from if I can do this. I don't know if I can really draw it well, but that's not too terrible. Anyway, this green line then, at that point, the green line is no longer a tangent. It is now, sorry, it is no longer a secant. It is now a tangent because it touches the curve on one point only. And that means the slope of this tangent line is the slope of the function at that point. We're going to need this result to derive derivatives, which are the heart and soul of chapter 2. But we have to get these 2 points infinitely close to each other in order for this to happen. In other words, we're taking a limit here. The limit as x approaches a will provide us with the tangent line or the slope of the function at that point a. Okay, and so yes, we'll save this knowledge now for the next chapter. We won't need it again just yet. So yes, so as we've already discussed in great detail, we have one-sided limits. Here, x is approaching c from the left. That's how you know from the little negative sign. Here's coming from the right. That's how you can tell from that little positive sign. But the limit, the original definition here is known as a two-sided limit because it implies that coming from the left and the right match each other. Okay. Okay. So in other words, this is the common limit of the left and the right hand side, one-sided limits. Okay. Now, let's get back to here. Now we're going to learn some algebraic rules for calculating limits. Okay, it's nice to draw the graphs and see how this works, but a lot of the time we will spend with limits, we're doing algebraic operations to come up with these limits. So let's take a look at a few of them right now. First of all, the limit of a constant is simply a constant. I mean, if the function is a constant, like, it could be something like this. Let's say we have the function f of x equals 3. That, of course, is a horizontal line. And you can see, I mean, what could the limit be other than 3? Okay. So if the function is always equal to 3, then the limit is equal to 3. Okay, that's what this is telling us. And we could choose any point we want. X approaches 0, for example. Oops, I forgot to use, no, sorry, I put equals. I should have put the arrow. The arrow means it approaches or converges to. I think I forgot to specify that earlier. The arrow means we're moving towards that point. We're not actually at that point. So we pronounce it approaches um, gets closer to converges to, they all mean the same thing. Okay, in other words, we're moving in that direction, either from the left or from the right, and we're getting closer to that value. How about um, oh, look, it looks like I did this twice for some reason. Okay. What about though? Oh, now here's an interesting one. Um, oh no, sorry, this is not what I wanted. My mistake. This is the limit of the constant. Here, the function itself is the constant. Here, the function is x. I didn't do this twice. This is f of x right here. Of course, this is the identity function. So let's say c is 0. As I try to approach 0 from the left, f of x approaches 0. And then as I approach from the left, function converges to 0. So if I tried 1, the limit would be 1. If c equals 2, for example, then the limit would be 2. So the limit in this case is just the constant that we are converging towards. And then if we raise that to some exponent, as you can probably imagine, if the limit that's equal to c, then that certainly stands to reason that the limit of x squared is just c squared. Okay, so in other words, if, for example, let's say I pick 2. So and this is, of course, x squared. That tells me that the limit of this function is just 4. Okay, no matter which direction I'm coming from, f of x is converging to 4 in both directions. Okay, so that's pretty straightforward. And that means it's the same thing is true if I have x cubed, x to the 4th. It doesn't make any difference. Oh, there we go. Okay. Now, algebraically, here's an interesting result. The limit as x approaches c of k times f of x can be written as k times the limit of just f of x. So, for example, the limit and then in turn, now remember the way this worked out, the limit of x squared as x approaches 2 is 2 squared. So that means here, all you're doing is substituting the 3 into for x. And so you've got 2 times 9, and you've got 18. Okay, so when it's the limit of a simple function of x like that, x squared, whatever, you're literally just substituting the constant into the function. And sometimes it's more convenient to be able to rewrite these limits. Here, maybe it helps, maybe it doesn't, but it's good to know that you can factor out that k, solve for the limit itself, and only at the end calculate multiply by k. This is very helpful when f of x is very complicated. When you have a complicated function like that, you're probably better off reducing it to the simplest possible form and then solving the limit with the simple form and then applying whatever is on the outside at the end. So of course, that implies that since the limit as x approaches c of x to the n equals c to the n, then if there's a k involved, we just multiply the result by k. It's that simple, just like we just did. Here's another nice one. So actually, I kind of left out a step here. And since this is the form x to the n, that means what I've got here is 32. Let's call this k. We need two different constants here. So basically, all you're really doing is using the constant. Oh, sorry. This should have said x. That's better. Now we're good. Okay, great. Now, what about algebraic operations on these limits? The limit of a sum of two functions is equal to the sum of the individual limits. Uh-huh. Or the difference, sum or difference. It's the same thing, which makes perfect sense. So how about this example? So these are both in the form, again, limit x goes to c. And so we break it up into a sum. We can treat this as the limit of 3x to the fifth plus the limit 2x to the fourth. In both cases, we're just substituting 3 into x, okay, because that's how this form works. Oops. Let's clean that up. And so you end up with, in the first case, 3 times 3 to the fifth. In the second case, 2 times 3 to the fourth. And you ultimately end up with 891. There you go. Now, here's an interesting one. This one is called the product rule. The limit of a product is the product of the limits. Couldn't be more straightforward. So here we go again. So this time, though, we're breaking this up into two separate limits. And again, we have this form. Actually, no, I wanted to use a k. Yeah. And so that means then that the first limit is 4 times 2 squared. I plug the 2 in for the x squared, and I still have the 4 here. And then here the 2 is replacing the x cubed. And so I end up altogether with 640. So if there's a product rule, that means there must be a quotient rule. And there is. The only thing we have to watch out for is that we must not allow the limit of g of x to be 0. If it is, then this is undefined. But for any other calculation, this works just fine. All right, so again, we've got that same format we keep running into. So it means the numerator going to give us 7 times 4 squared. The denominator will be 3 times 4 cubed. And you can see that leads us to 112 over 192, or 0.583 approximately. Okay, and then we also have the so-called power rule, where if you have the limit of a function raised to some exponent or other, we can rewrite that by taking the limit of f of x and then raising that result to n. So let's look at the example in the next slide. Limit of 5x to the fourth is the same thing as the limit, the entire expression limit 5x to the fourth. So in other words, what you're basically doing here is, instead of evaluating this directly, which you certainly could do, what you're really doing is you're trying to simplify it a little bit by solving. You're actually now just evaluating the limit of 5x as x approaches 1. And then when you're done, you can take the entire expression and raise it to the fourth power. In a case like this, it didn't really speed up anything. Here you would have had oops. And really, that's exactly what's happening here too, because you're just saying, well, listen, we know that the limit of 5x is just 5, and when we raise that to the fourth power, we're going to wind up with 625. Ooh, now what about this one? Well, here we may end up needing multiple rules to solve for this one. For sure, we can use the sum rule, which we want to do. But so in other words, at the very least, let's do this. Oh, the second one is a constant. Now here, recall, so we'll use that property. This term can therefore be rewritten, as you can see here, as 4 times the limit of x squared. And over here we have a constant. And so we're going to end up with 3 for this term. Here we have 4 times. Actually, let me move this over here. And then, of course, just this piece, the limit of x squared as x goes to 2 is 2 squared. And then here we have, this is a constant, it's just 3. And then when you evaluate it, you eventually end up with 19. Okay. Now, what's coming up next? There is an extremely formal definition of limits that is very complex and very difficult to wrap your head around. Um, this definition by Cauchy is called the delta epsilon limit. I've included it here in case you want to read it, but we don't need it for what we're going to do. In other words, it's something you should be aware of, that there does exist such a definition. It's a very complicated thing to think about. Basically, what he's suggesting is that if a limit exists, that means, let's say you have something like this going on. What he's basically saying is that however close we get, we're guaranteed to get even closer here to 4 if the limit exists. Okay. So I find it's like, it's a very, very complicated way of expressing this. It's very abstract. And you're welcome to read this if you want. But I don't think we want to get bogged down in this right now. I mean, maybe we can come back to it later on, but if you do find yourself in a much more advanced class, once you get past Calc 3, a lot of the classes you'll be taking in math major will require you to do some proofs. And that's the level that you really need to be, where you start to take advantage of these types of definitions. But for our purposes, we're just trying to learn how to calculate limits. So I think we can leave this for anyone who wants to go through it. And we can now move on to the next section of this limits chapter. So let's see what's coming up next. So remember, this chapter has been split up into 3 parts. Part 2 is right here. Part B actually is what I should say. And it's called, as soon as it wakes up, we're going to see using the rules. Well, basically, this is what we're sort of getting into. We're showing you the rules, and now what we're basically going to do is show how the rules can be combined within the same limit to come up with the correct solution. For example, this one, well, now it's going to seem like a breeze compared to what we've been doing. The limit is x approaches -3 of 4x plus 2. We can break it up first into a sum, or a sum of 2 limits. Let's put this up here to remind ourselves where we started. The limit of x as x goes to -3 of 4x plus the limit of as x approaches 3 of 2, -3, sorry. And then I've factored out the 4. So that's where this comes from. This stays the same because it's a constant. And so here, you're basically just plugging in the -3 into x. This is a constant, so that's actually our limit. So we're going to end up with 4 times -3, okay, plus 2, and we end up with the final result of -10. So we basically applied a couple of different properties here to come up with our answer. Now, it turns out this wasn't absolutely necessary. What you could have also simply done is, because this is a polynomial, you could literally just replace all the x's with this -3, and you still would have gotten the same answer. But this is what's going on behind the scenes. Okay. So in other words, when you get some practice with these, you'll see that in many cases, direct substitution will give you the limit that you're looking for. But it's important to know what rules are going on that justify or enabling us to do this. Okay. What about this one? Oh my God. Well, again, we can break it up into many individual pieces. Um, so let me just put this here to remind you what we just did. So you remember we have the sum and difference rules, we have the quotient rule. So you can see how this turns into this. And then in addition, the limit of 2x squared became 2 times the limit of x squared. Negative 3x, that's now the negative 3 times the limit of x. This is just a constant. This is just a constant. And this just stays at the limit of x cubed. Now we do our substitutions. And we end up with 2 times 4 minus 6 plus 1 over 8 plus 4. Was that 3/12 or 1/4? And again, if once you get comfortable with limits, what you could do is literally just substitute directly. And you'll end up here with 8 minus 6 plus 1 over 8 plus 4. It is the same. Okay. Oh, but look at this disaster. Oh. Okay, not a problem. We'll break it up into a product. And let's see, let me copy this to the next slide. And so, yes, so we break it up into the two parts. Now, because these are polynomials, at least here under the square root sign, we're just replacing the x's with the 6, and you do eventually end up with 11 radical 10. Okay. Now, later on, we're going to expand our ability to take limits. We're going to see what happens when we take limits as x approaches, for example, infinity or negative infinity. And of course, then we have to approach it a little differently because we cannot use direct substitution, right? So also, sometimes we end up with division by 0, and we have to figure out what to do about that. So these are the basic straightforward cases where we're essentially just solving for a particular constant. But we'll see as we go along that when the limits become more complicated, we have to approach them a little bit differently. Now here's one that says, oh, so remember we defined a rational function as a ratio of two other functions. And so here, what it's essentially telling you is that you can just directly substitute c for x, as long as you do not end up with division by 0. If you do, we have to try something different. Like this one. Now, it's kind of a mess, but it turns out, if you notice in the denominator, substituting directly 0 into x will not lead to division by 0. So we can break it up into individual pieces, or we can directly substitute 0 for all these x's, and we'll end up with an answer. Right. So here I went through the formality of breaking it up into these separate limits and then evaluating each one individually. So this is 0 cubed, 0 squared, This one is a constant, so it stays at 5. Here we have 2 times 0 squared minus 0 plus 4 5/4, and that's it. We're done. Now, what if we did get division by 0? Oh, now we could just say, well, listen, that's it. We're done. We can't do this. But there are ways, possible ways of working around this. Now, this is a little bit more involved. I'll tell you what, I didn't realize it was so late. I think this might be a good stopping point. Right now, you already have the ability to do a large number of basic limits, and you should actually be able to already start the homeworks, which are due on the 16th. I don't remember exactly which ones are in there, but you can certainly already attempt a large number of them as just after this session. What we're going to do here is look at strategies for handling more complicated limits. And by the way, this topic won't just disappear. As we get deeper into the course and introduce more complex concepts, we'll see that we'll be able to expand the number of limits that we can calculate. But here we're covering the basics. What we're going to see later on in this chapter is, what do you do if you not only have division by 0, but look at this one. You actually end up with 0 over 0. What do you do then? We're going to learn how to do that in this chapter. That creates what's called an indeterminate form. And so what will start to happen is when we start doing limits more and more, we'll see that when we run into these strange cases, there are strategies that we can employ to come up with the correct answer. This is just one of them, by the way. There's several others, and we'll run into them as we go along. But right now, I think we've had enough fun with limits for one day. We'll start here with a special case the next time that we meet, and then we'll just take it from there. And then fairly soon, we'll be ready for chapter 2, which is where we start to look at derivatives, which really is, in my opinion, the most important chapter in the book. And that's going to take a while. Okay, there's a lot of techniques to learn. And so that's where we're going to really get deeply into this material. But you'll see when we get there that the derivatives themselves are defined in terms of limits. So that's why this has to come first. All right, anyway, so I think I'll stop it here. And then the next time we meet, we'll be looking at more complex limits. And then fairly soon after that, we'll start introducing derivatives. All right, so I'll see you then.